Good evening, everyone, and welcome to the Bridges Lecture Series at St. Jerome's University. My name is Bob Lemieux. I am the Dean of Science at the University of Waterloo, and I'm pleased to act as moderator for tonight's lecture. The Bridges Lecture Series aims to overcome the gap between mathematics and arts and the humanities. And this is the fifth year of this important series. That is a joint effort between the University of Waterloo faculties of Mathematics and Arts and St. Jerome's University. For the remainder of this season, we're also pleased to partner with the Fields Institute for Research in Mathematical Science, who provided the extra funding necessary for this season. Also supporting tonight's lecture is the Department of Fine Arts, which contributed additional funding, space, time, materials, and most importantly, students who created these machines that you see up front here. That will be the focus of tonight's lecture. And tonight's lecture is entitled The Harmonograph. And it's my pleasure to introduce our two very distinguished speakers who will speak on this important topic. Our first speaker who will begin tonight's lecture is Anita Chowdry. She is a London-based visual artist, researcher, and educator whose work is inspired by mathematics, geometry, and the book arts of the Islamic world. She's interested in the history of practical science and technology and how it has shaped the arts and our aesthetic sensibilities. Her work is underpinned by an engagement with process and materials and includes metalwork, etching, drawing, painting, and mineral and metal-based pigments. The Iron Genie Harmonograph project was developed between 2012 and 2013 for Anita's MA in Art and Science at Central St. Martin's College of Art at the University of the Arts in London. The Iron Genie has since toured institutions in the UK, including the Museum of the History of Science, Oxford, and Dulwich Picture Gallery, as part of a major retrospective of the work of M.C. Escher in London. Following Anita will be John Baez, who is a mathematical physicist educated at Princeton and MIT. John is now a professor of mathematics at University of California, Riverside. And during the summertime, he also works at the Center for Quantum Technologies in Singapore. Until recently, John worked on higher category theory and quantum gravity. But in 2010, concerned about climate change and the future of the planet, he switched to working on more practical topics and started the Azimuth Project, an international collaboration to create a focal point for scientists and engineers interested in saving the planet. So, without further ado, I will invite Anita to come to the stage and begin our presentation.
Thank you very much. And I am very, very happy to be here. And I would like to very quickly, before I begin, I can hear a bit of a buzz happening here. Is that okay? I'd like to thank Benoit Charbonneau for inviting me to take part in this, and I would like to thank John Baez for recommending me. And I would like to thank Linda Carson for all the hard work that she's put into the logistics of what was quite a complex project this week. And I want to say a very special thank you to the team of students who have worked extremely hard all this week to produce these two excellent kinetic working harmonograph sculptures, which everybody will have a chance to use at the end of the presentation. So please come up at the end of the talks and have a go at doing some drawings and producing something really cool, like the drawings you saw on the, hopefully saw on the whiteboards at the back. And the students will be standing by to help you and explain how they work. And we, particularly the students and myself, would like to say a very, very special thank you to Adam Glover, who is the technician in the shop in the Department of Arts and Design, because without his support we would not have been able to build these. So I really feel it was important to acknowledge his input in making all this happen. So without more ado, I will begin on the talk. You may be wondering what the Iron Genie is. Well, I couldn't bring the Iron Genie. The Iron Genie is, this is a maquette, it's a model, and it's a 2-meter high harmonograph made of steel. So it's like a big, over-the-top, fancy version of the harmonographs you see here. So these work in exactly the same way, they're just not quite as macho. So I brought this just to show you. So I'm going to put it over here on this, one of the harmonographs. I did, my first interest in the harmonograph was simply looking at these wonderful drawings. I came across these lovely drawings and thought, that's really cool. I wonder how these drawings were produced. And I realized that they were produced by machines that were created during the 19th century, invented and created as part of perhaps the scientific fun of gentlemen scientists, builders, mathematicians, engineers. It was always quite a recreational thing to have produced these machines. And they have a very fascinating history. Basically, it's a pendulum-driven device, and the pendulums move, and some of the pendulums have pencils attached to them, and some of the pendulums have paper platforms with paper attached to them, and when the pendulums move, the pencils are driven by the pendulums to make these amazing pictures. And John will actually explain this a great deal better than I can, but I'm just going to touch on the history of the harmonograph. This is just a portrait of the Iron Genie. If you can just see, it's got a few, it's made of metal, it's quite big, and it's quite a good museum piece. The idea for the harmonograph comes from studies of the frequencies of pendulum movements. And I've just got a few quick facts on pendulums here, but I'm not going to go into them in great detail, save to say that the harmonograph relies on some of the facts of pendulums. So, for example, you will see that these are pendulums which have a pivot, and then they have a weight, and the pendulums will swing at specific frequencies which are determined by how much distance there is between the pivot and the weight. So the longer that distance, the lower the frequency, and the shorter the distance, if you look, if you get to see this one of the weights is right up very high near the pivot, the higher the frequency. And the idea of the pendulum came initially from the rather reprobate activities of a gentleman who went on to become professor of, or chair of mathematics at Glasgow University, called Hugh Blackburn. And when he was at Cambridge, he used to go out carousing with his good friend Lord Kelvin, and the two of them would come home roaring drunk, middle of the night, to their rooms in Cambridge. And Hugh Blackburn had set up a funny little pendulum thing, not a proper pendulum, but a loop attached to two pivots from the oak rafters of his rooms, and then another pendulum suspended from that, which swung at a different plane from the top loop, and they used to sit on this little swing at the bottom, and they would swing around, and it went in all sorts of funny shapes. And this was just something that they did as reprobate young men having fun, but in fact it was the source of the idea of the harmonograph. So I think it was born of fun as well as science. So that is now known as a Blackburn pendulum. We didn't have a chance to make it. We didn't actually have the time, but it would be fun to make one. In fact, there are artists who have used those. At the same time, another scientist, Joule Antoine lissajous, was doing experiments in order to see if he could get a visual representation of sound waves. And he gave a very famous series of demonstrations and lectures at the Royal Institution, which were recorded and commented on greatly. And in this experiment, basically, a thin point of light is directed onto the tip of a tuning fork, and on that tip there's a mirror. So the light is then bounced off there onto the second tuning fork, where there's also a mirror attached. The tuning forks are beaten, so they start to vibrate at different frequencies, and the combined frequencies are projected onto a dark screen. And these lovely shaped figures he catalogued, and they came to be known as lissajous figures or lissajous curves. So they're visual expressions of combined sound frequencies. By the same token, the pendulum is a metaphorical mirror of the idea of sound frequencies, on account of the fact that the frequencies vary depending on the length of the pendulum. And some artists have tried to equate specific lengths with specific musical notes. So a relationship was seen very early, which is why it's called the harmonograph. Same time, or a little bit later, we have a gentleman called Hubert Airy, who was again wasting his time, not carousing, getting drunk, but he was a physician and a country boy, so he didn't do reprobate things like that. He went for long walks, and he sat and he daydreamed and did nothing in particular. And he wrote this wonderful article in Nature magazine of a time when he sat looking at a tree that had little twigs growing out of it, and he was just idly going, sort of pinging the twigs. And I always think it's a bit like this bored school kid in school with the ruler going and watching the vibrations. And he was intrigued by the vibrations, and so he took a piece of paper and he attached it to some other twigs above the vibrating one. He attached a little pencil to the vibrating twig, pulled it, let it vibrate, and he got a pattern like that, which he published. And so he did quite a lot of drawings. He made possibly the first combined pendulum himself. We don't know exactly what it looked like, but this could be arguably the first set of harmonograph drawings based on his exploration of how pendulums and twigs vibrate. It rapidly became a subject of conversations and evening meetings and boys with their toys. And I found a very, very interesting book from the 1890s, which is by a gentleman who became, for 1 year, chairman of the Norwich Gossip, is it Norwich Science Gossip Club. And they had regular meetings, which they called Conversaciones. And I love the idea of these upright gentlemen. They may be professors, they may be scientists, they could be engineers, they could have been building bridges during the day, or coal mines or whatever. They could have been respectable parsons who escaped to do their gentleman things, which is nothing as dubious as one might think. They were getting together and deciding what would be the next new interesting experiment to do. So this book is a privately published book about how he had made a two pendulum harmonograph, or a lateral pendulum harmonograph, according to one that was made by Tisley and Spiller, who were a firm of scientific instrument makers, and which in turn was made according to Hubert Airy's experiments. So there is a kind of narrative that progressively goes through the 19th century. The drawings in this book are all actual original drawings made on the harmonograph they built, and we've built something like it. And I'll just quickly descend here just to demonstrate. This is a lateral pendulum harmonograph. So the pendulum, you'll get a better look when you come here. The pendulums each go in only one direction, so they move laterally. That moves back and forward. This one moves back and forward at right angles. And when you put the pen down, it does drawings like that. Take my word for it for now, but don't take my word for it later. Come up and actually have a go at making it. So this rapidly became so popular that one of the leading firms of scientific instrument makers, Newton and Co., began to produce them commercially, i.e. they could be bought by enthusiasts who were interested, and they were developed in several different kinds of designs. Now this is basically the lateral pendulum, the lateral harmonograph, which is that one, and then other ones were designed which did much more exciting things. This is based on Benham's rotary pendulum, and what it has got is got one pendulum mounted on a gimbal, so it goes round and round and round, and then the pen is attached to two lateral pendulums which can be manipulated to go round and round and round. So it's called a rotary pendulum harmonograph. So that's just shorthand for differentiating between the two types of harmonographs. I do love their advertisement. Makers of philosophical instrument makers by special appointment to the Royal Institution of Great Britain, makers of scientific apparatus to the Admiralty and the War Office, etc., etc. So they were extremely, highly thought of business. These were the pendulums, the harmonographs they produced were luxury items. That one would set you back about £10 and 10 shillings, which in 1909, when we believe this book was produced, was quite a lot of money. Obviously, luxury goods. And I have darkness. Okay, that's better. So here's an image just to give you an idea of the two different kinds of drawings you get from the two different kinds of harmonograph. So this is the lateral pendulum harmonographs. You get these lovely sort of fish shapes, and then the rotary gives you these much more circular shell-like shapes. I love the fact that they're very reminiscent of natural forms of creatures and other natural forms. So, what were these? Why were these devices invented, and what was their purpose? Curiosity, I believe. Not only did these extraordinarily gifted gentlemen produce pendulum-driven drawing machines, but they also started to produce ones that were driven by gears. So although the gear-driven drawing machines are really a different class of drawing machine, it's still about drawing curves, and they went by several names. Sometimes they were called geometric pens or geometric chucks, all sorts of names. But basically, you got these wonderful contraptions put together with gears to produce lovely oscillations, the combined oscillations of which produce these cool drawings. Now, this obsession continues to today, and I'm not the only artist who's become very fascinated by curve drawing machines and 19th century technology in general. This image up here is produced by a Blackburn pendulum. That's the combined pendulum that Hugh Blackburn swung around on. It has a pulsating lead at the bottom, lead light, and the image is projected onto a piece of light-sensitive paper. And this series of images are made by an American artist called Paul Wainwright. Here is another Hungarian but living in Britain artist who's got a very simple pendulum device, but it's produced over an overhead projector. So you get these lovely happening images happening on a wall. A professor of philosophy in the 60s who'd served in the RAF during World War II bought up the analog sperries or bomb sighters from aircraft, and he turned them into drawing machines that produced similar class of drawings. So there's quite a lot of interest. One wonders why do contemporary artists even now want to look back to 19th century technology? There's been quite a lot of discussion about it, and I think it's something that goes alongside the great advances that have been made in digital technology. There's been a lot of interest in development in digital art, and I think alongside that there's a desire to go back to the roots, to explore a new analog technology, the basis from which everything that we are now was born. There's also a very visceral human interaction with analog machines. People can go up to them and actually see how the science works. There's no secrets behind a screen. It's all there out in the open for you to touch, feel, and experience. And I think that's part of the appeal. So that's my prototype, which looks remarkably like the Waterloo students' prototype of a rotary pendulum here, except that's much more handsome because it has been styled, and you will see some very elegant styling and piano keyboards, lovely shapes. So they're kind of chic furniture as well. My interest also came because of my general interest in natural forms. So I love working with flame fractals because they're very organic in the forms they generate. I'm interested in classical geometry in the way in which it mirrors natural forms. So I was just going through very quickly a few slides. This is as much as anything to show the students how one can take a prototype and develop it into a sculpture, into a concept, into something that you might create as a large piece of public sculpture. My inspiration for the Iron Genie harmonograph, for example, was because it was Victorian. The place where it was made was King's Cross in London, where there are two stations which are temples of Victorian engineering and the confidence of Victorian engineering. This is St. Pancras Station. It's utterly uplifting to walk through it, looking at all this high Victorian ironwork. And the fact that this represents an age when technology was based on iron and steam and coal, hence the choice of steel to make the harmonograph. I wanted to have this theme going throughout the development of my harmonograph, so I used classical Victorian drafting methods. It was part of the whole thing. The whole joy of sourcing Victorian drawing tools, delicate little instruments, and hand drafting all the parts so that the people that were working with me, the technicians, could read those rather than nice sort of CAD files. I had to learn new skills in order to realize the concept of this Victorian piece of harmonography, shall we call it? So I had to learn metalwork skills. A lot of the energy, it had to be steel, it had to be brass, it had to be craftsmanship, which is partly why the artwork took so long to realize. Central St. Martin's has a very good metalwork department. So these are just a few images of having fun with machines. And I do recall this week the sheer joy that many of the students experienced when Adam explained how to use a machine, and you saw the first time somebody was using one of the machines, the sheer empowerment and exhilaration. And I was so happy to see that, because that was very much what I experienced the first time I was let loose in the metal workshop with some screaming angle grinder and sparks flying everywhere. It's part of the joy of making art, is the process of fabricating. Materials are very important. I did spend a fortune on brass because I did want it to have that Victorian crafted look, which becomes by definition, whether you like it or not, steampunk, because that's the kind of buzzword now. But I think what steampunk does represent to a lot of people is that kind of slightly nostalgic retro science fiction future that never was kind of aesthetic. And it does seem to have a certain a vibrance today. It has it resonates in a particular way today, which is interesting. The other thing that was very exciting and is exciting when finding places where you can get your sculpture made is finding the human expertise. There are very, very few people left from that generation, those generations of old school engineers who have the old school hand lathe techniques. And we were lucky to have a technician who could do it. So again, I thought, well, let's make the most of the resources we've got. And so I bought a great big expensive hunk of machine quality brass and asked him to turn the finials which adorn the top and bottom of Iron Genie. And I was told by his colleagues that he walked around carrying the brass like a baby for a couple of days before he started using it, which is very, very touching indeed. A lot of processes went into it, including traditional, the bezel, the mirror bezel traditionally hammered. Wonderful, again, to have this engagement with materials where you anneal brass, it shines with all these wonderful colors. The plain ordinary mirrors just wouldn't be good enough, so I had to learn how to gild a piece of glass with precious metals, so I used palladium to create something much more exciting than an ordinary shaving mirror. So that's slightly distressed surface, slightly grey surface, is palladium leaf. The tabletops of the Iron Genie were zinc plates etched with designs that are reminiscent of natural forms. So one of them has a flame fractal. One of them has drawings that were scanned from the prototype. And the third one had actual natural geometry in the shape of fern leaves embedded into soft ground, soft etching ground. And I used those techniques to create these beautiful etched zinc tabletops. Now, etching is interesting because etching originally was developed in the Middle Ages to decorate armor, to decorate steel armor. So before it was a printmaking technique, it was actually a technique of embellishing metal objects. Those are a few prints that were taken off it. And finally, still in the same location, King's Cross, there happened to be a Victorian church with a really lovely crypt where we did the filming of the Iron Genie as soon as it was made. And the film can be seen on Vimeo online, and I do have some cards so you can get access to that. It's been quite a star at a number of institutions. We did want to bring it here, but we found the logistics and the sheer price of crating and shipping the Great Hulk, which is what it basically is, was just prohibitive. So we had the much better solution of our trusty team of brilliant students and our technician and our two homemade Waterloo University harmonographs. And there I'm going to stop. Thank you very much.
Thank you, Anita. And now we'll invite John to come to the stage and present the second part of this lecture. John?
So let's see if I can operate this. So somewhere here is my talk. Yes? Oh, good. So it turns out that the electronic technology is much more fragile and delicate than the old Victorian analog technology. So this talk is much more likely to go crashing and burning at some point than these machines, which says something. So I decided to give my talk the sort of suspiciously new agey sounding title of Harmonic Vibrations, because that's the title of a book on the harmonograph, which Anita showed me. So if you know about New Age beliefs, there are people who like to talk about the vibrations that they're feeling from crystals and other objects. So the interesting thing is that while a lot of what they're talking about is a little bit silly in the sense that they're using scientific vocabulary to describe what's probably a really real but psychological phenomenon rather than physical phenomenon, there is a truth to it in that the universe is made out of vibrating objects. And the origin of science has a lot to do with the discovery that harmonic vibrations rule the world. So sometime around 500 BC, this fellow named Pythagoras, about whom we know extremely little, is credited with noticing that there's a connection between mathematics and harmony. This is a picture of him at work made centuries, or I guess about a millennium later, so it has nothing to do with how he actually looked, no doubt. But what he noticed apparently is that strings that have simple ratios of their lengths will make harmoniously pleasing chords when you pluck both of them, as shown in the picture at left. And the reason why that's the case is in part due to what you see over here at right, which is that a string can vibrate in various ways. It can vibrate at its so-called fundamental frequency. That's this lowest frequency at upper left here. But then it can vibrate at higher frequencies. So here you see 2 or 3 or 4 or 5 or 6 wiggles. And the one with 2 wiggles will be vibrating twice as fast, it turns out. And this will be wiggling 3 times as fast, 4 times as fast, 5 times as fast, 6 times as fast. And it turns out that notes that have these nice, simple ratios of frequencies actually sound harmonious, and that the different kind of pleasant chords in music are precisely coming from, notice the technology broke, so the mouse needs a little, I think you need to stroke the belly of the mouse. Could you show me how to Oh, push the button, push the belly of the mouse, okay. Okay, so now where's the cursor of the mouse? Connection lost. Yeah, I warned you. Okay, quick. So if one thing oscillates exactly twice as fast as another, together they make an extremely pleasant chord. In fact, it's so pleasant that musicians don't consider it a chord. They call it an octave. And so the ratio of frequencies there is 2 to 1. But there are other important frequency ratios, like 3 to 2, which musicians would call a fifth, or 4 to 3, which they'd call a fourth. Don't worry about those terms if you don't know them, but they're just the basic chords that you hear the most commonly in simple kinds of music. But whereas complicated ratios, for example, something like 23/17, sound jagged and dissonant to the ear. So Gottfried Leibniz, the philosopher around 1700, said, "Music is the pleasure that the human mind experiences from counting without being aware that it is counting." So you may think you don't like mathematics, but your ear has different opinions. It's somehow a mathematical entity in its very nature, and the things that naturally sound good are the mathematically simple frequency ratios. So by the Middle Ages, people had made considered there to be 4 mathematical arts: arithmetic, geometry, astronomy, and music. Those were the quadrivium, the 4 mathematical arts. And so they linked all these concepts, and they imagined that because the planets are going round and round, that their vibration should be making some kind of music, which naturally we can't hear, but maybe nonetheless some type of music, which they called the music of the spheres. The person who seems to have taken that the most seriously that I know of is Johannes Kepler, who's very famous for his work on astronomy. In 1619, he published a book called The Harmony of the World. This is a picture from that book, which you can actually get a copy of online now. And here, what he's doing was noticing that as planets move faster and planets will move faster and slower as they make their orbits. He was, in fact, the one who, in this book, who realized that planets go not in circles but in ellipses and go faster when they're near the sun and slower further away. So that's what he's famous for. But he was also doing considering these ideas, which now seem quite flaky, namely thinking that because when the planets are going faster near the sun, they would be making a higher pitched note than when they were going slow. And so these here are the tunes produced by the various planets. And I think the very last one there, my Latin is no good, but I just happen to know that last one says, and the moon also makes some melody. And so that's the melody of the moon, according to him. Kepler is a really remarkable guy in that he had a mixture of ideas which we would consider completely far out and crazy and mystical, but also is one of the most important scientists, and it was his discovery that the planets go around in ellipses which led Newton to realize that the gravity is a force that decays with the inverse square of the distance, and to formulate his laws of mechanics. So indeed, as physics developed, it became very clear that you could use the same kind of mathematics to describe many different kind of oscillating objects. The universe is full of oscillators. So there's the pendulum, which is the basis of the harmonograph. They're vibrating strings, which is the basis of a lot of musical instruments and Pythagoras' theory. But also if you have a pipe with air, like a flute or a horn, the air inside the pipe will oscillate. That's what these three things are showing, three different vibrational modes of an open tube, and that's how you make music with wind instruments. And then also, if you have a mass hanging on a spring, it will also carry out an oscillating motion. And the mathematics governing all these different oscillators is essentially the same, and is sort of one of the basic things you learn about in a course on modern physics, or classical physics. So going back to how it developed, so in 1602, it was Galileo who noticed something extremely important, which is that, roughly speaking, how long it takes for a pendulum to swing back and forth does not depend on how high it swings. That's not exactly true, but it's close to true if the swing is not too high. So we say the period of the pendulum, that's how long it takes to swing, doesn't depend very much on its amplitude. That's a very useful fact because it means if you build a clock using a pendulum, if the amount of swing changes just a little bit, it will barely affect the rate at which the clock ticks. Of course, you need some machine to keep the pendulum swinging back and forth, so you can make some elaborate contraption out of gears and weights where the slow sinking of the weight keeps powering the pendulum swinging. But using this fact about the pendulum, that its period doesn't depend much on its amplitude, you can make a very accurate clock that way. And Galileo had the idea of making a pendulum clock this way, and he tried to make one, but he actually went blind in his later years and was not able to carry it out. But later, Christian Huygens, another famous physicist, actually built the first pendulum, apparently based on Galileo's design, in 1652, and this was the most accurate clock of its day. And as you probably know, if you've seen grandfather clocks, that's a technology for clocks that for quite a while was the best technology for clocks. Now we do fancier things. We may have like a quartz crystal watch where a tiny little microscopic crystal of quartz is oscillated by means of some electrical impulses. So it's a different kind of oscillator that we're using now in more sophisticated kind of clocks, but it's still an oscillator. And even atomic clocks, the most accurate clocks we have now, are just using the oscillation of an individual atom to do essentially the same thing. Now, what the physicists realized that was very interesting here is that there's an important connection between all these oscillatory motions and the concept of a circle. When you have something oscillating back and forth, like this mass at left, both its position is oscillating, but so is its velocity. When its position is at its extreme point, either furthest down or furthest up, for an instant, its velocity is zero. It momentarily comes to rest at either of those points. So if you graph its position vertically and its velocity horizontally, and use this line here to mean the zero velocity, when the particles, when the mass's position is at its bottom or top point, the velocity is zero. But conversely, when the object's position is halfway between top and bottom, that's when it's moving the fastest. So over here, the velocity is as high as possible, and the position is intermediate between the top and bottom. So if you plot both the position and the velocity together, you get a point going round and round. And the beautiful fact about a harmonic oscillator, which is the simplest kind of oscillatory motion, is that this point here, this green dot here, will go around in a circle, or perhaps an ellipse. If you stretch your, if you stretch things, you'd get an ellipse. It's just a stretched version of the circle. So where does this ellipse live? Well, it doesn't live in ordinary space. Ordinary space, that is what you actually see, is over here, and you have an object moving back and forth in just one direction. It's living in what physicists call phase space. The origin of the term phase space is fairly obscure, so I wouldn't advise you to worry about what the word phase actually means there. But what it is it's a space which has both position in it and velocity. So if you keep track both of the position of something and its velocity, you're describing a point not in ordinary space, which would just be the position, but in this abstract space called phase space. And that's the way of thinking, I think, that separates physicists from ordinary people, is that physicists spend a lot of their times living in phase space. So if they look sort of phased out, then you know why. And my mother used to say it was always just a phase, but she didn't know how long it would last. So here's another way of thinking about things, just sort of turned around. If you start by thinking about a particle moving around a circle, you can think about separately its height and how its height changes with time. And if you graph that as a function of time, you get a wave motion. Or you can think about its position to the left and right, and you could graph that. And here, just using some cute little trick of a quarter circle, that graph has also been drawn horizontally. I would have drawn it vertically, but I'm not good enough at programming, so I just stole this picture from the internet, actually from Wiki Commons, where it's in the public domain. And so a motion of an object around a circle contains within it two separate oscillators, two separate oscillations, which in the previous slide were the position and velocity of a particle. When you go to high school and you're forced to learn about trig functions, that's what they're really trying to teach you, although I think very rarely with complete success. They're trying to tell you that there are these two things called the sine and cosine, which are just names for the vertical and the horizontal position of a dot on a circle. So trigonometry is really not the study of triangles, it's really the study of thinking about something going around in a circle and how its vertical and horizontal position depends on this angle. So this is just, again, the relation between an oscillator, something wiggling up and down in real space, and a point moving around in a circle in phase space. So this is why they make you learn trig. They're hoping you might become a physicist someday and use this for something. Now, I should admit that the pendulum is not really a perfect harmonic oscillator. As it swings higher, its period becomes longer. It's very evident when you get swinging almost up to the top. So I'm sure every child who's swung on a swing has contemplated the possibility of swinging all the way over or just to the top. And although no child has survived to actually do that and report back, nonetheless, we know that when we get fairly close to that, it takes longer for the swing to swing. So for very short swings, the period doesn't depend much on how much this swing swings, on the amplitude. But as you go towards this completely vertical point, the period becomes longer. And also, if you plot the position and velocity as a point in phase space, which are those little pictures up on top, you see that if the motion is small, the path traced out in phase space is almost a perfect ellipse, but then when it becomes a very high swing, you see it noticeably deviates from an ellipse. That thing up, red thing at upper right there is pretty far from an ellipse. It's sort of pointy. So the math that describes a pendulum when it swings fairly high is more complicated than the mathematics of harmonic oscillators. It's a branch of math called elliptic functions, which are more sophisticated than trig functions. And it's very interesting, but that's not really what I mainly want to talk about. There's another important complication of real life, which is that in real life there's always friction in a pendulum, and so the pendulum doesn't swing back and forth forever. It gradually slows down. And when you start making some pictures on these harmonographs, you'll see that that's another very important factor, that it starts out tracing some curve, but then the curve slowly shrinks as time goes by due to friction. So that's another complication of real life. But in 1857, Joule Antoine lissajous had this brilliant idea that Anita mentioned of bouncing light off of two tuning forks at right angles to each other, tuning forks vibrating at different frequencies, so that the vertical position of this dot of light would be oscillating at one frequency, but the horizontal part would be oscillating at another frequency. So now we're no longer in the realm of just a single oscillator, which is what I'd been talking about up to now. Now we have a machine that's built up out of two oscillators. And you'll be able to play with one here with two pendulums doing essentially the same thing, tracing out essentially the same type of curve, but using pendulums instead of tuning forks. What was so beautiful about this experiment is it took Pythagoras' insight that pleasing chords correspond to simple ratios of frequency and let you actually see the oscillations of the tuning forks as traced out by these curves, so that you could see from the shape of the curve what the chord was. And I'll explain here that different frequency ratios give different characteristic patterns, which are now called lissajous curves. So here is an example of a curve that can be formed when you have something moving back and forth, vibrating back and forth at some frequency, but moving up and down at twice that frequency, which is why there are more up and down wiggles than crossways wiggles. So if you have two tuning forks that are in an octave apart, and you do lissajous experiment, the light would trace out a curve like this. Whereas here you have one that's vibrating 3 times as fast, does 3 vibrations up and down for every 2 vibrations across. That's the ratio that's called a fifth, another very nice chord. And so you could see those different chords. And so as Anita mentioned, and later in 1874, this fellow Tisley described a device built from 2 pendulums, each one of which can only swing in one direction, but these 2 directions are at right angles to each other. So that's basically this device right here. And that's called a lateral harmonograph. And the idea is that the motion of one pendulum moves the pen, and the motion of the other pendulum moves the pad of paper. And so then if you have 2 pendulums that you have oscillating at a frequency ratio of, for example, 3:2, it will draw exactly the same type of curve that lissajous drew with light. Here, you'll notice it's a little bit fancy. There are lots of these curves. That's because it's slowly the curve is slowly shrinking as time passes due to the friction slowing down the pendulums. So instead of the simple thing the simple mathematical thing that I showed you here at right, you have a more complicated pattern because you have to draw something like this over and over again, and it slowly shrinks. So you get some extra fanciness coming from the friction. So now you see what we've got here is 2 pendulums. So I said the position and velocity of one pendulum would trace out a curve in a 2-dimensional space, because there are 2 numbers, position and velocity. When you have 2 pendulums, they'd be tracing out really a curve in 4-dimensional space. There's a 4-dimensional phase space where it keeps track of the horizontal position of the pen on the paper, the horizontal velocity of the pen on the paper, but also the vertical position of the pen on the paper and the vertical velocity of the pen on paper. So a 4-dimensional space is hard to visualize, and indeed you don't really see it directly when you see what the harmonograph is doing. The harmonograph is just drawing a two-dimensional image because the harmonograph's drawing involves the position of the pen. So the horizontal and vertical position of the pen are just two numbers. So you see this two-dimensional curve. But really what's going on is that two-dimensional curve is a kind of shadow or projection of the full story. And the full story is going on in twice as many dimensions. It's going on in 4 dimensions. So just as I said that the full story in phase space of a single pendulum is a circle, and then if you just keep track of the position, you have a motion in 1 dimension. Here we have the same kind of thing going on, but with twice as many numbers. So at some point, some people, when they get to hearing about 4-dimensional geometry, they say like, okay, I'm going to quit now. I didn't want to know that much geometry. But for mathematicians, then of course, they have the exact opposite reaction. It's just like, wow, this is some really bizarre thing. I really want to get into it and study it and see if I can think about 4-dimensional geometry. And so most mathematicians spend a lot of time trying to think about that, which is why they bump into walls and things. Because they're not really there. So now there are like other ways to combine multiple pendulums that yield much more complicated results than this harmonograph. They can yield what are called chaos. So here, both at left and at right, what we've got are pictures of a pendulum hanging from another pendulum. Actually, a solid rod hanging from a solid rod with a hinge. As they swing, they can do extremely elaborate things, as you can see from the motions that they trace out. These are nowhere near the beautiful, simple, smooth curves of the lissajous figures. These are a big, complicated mess. So that's called chaos. And so again, what's really going on is that there's something going on in 4-dimensional space, phase space, where you keep track of the position and the velocity of each of the 2 pendulums. But these tangled up curves that we see here are projections of those curves in 4 dimensions down to 2 dimensions. That's partially why they're able to look like such a mess. They're not so messy up in 4 dimensions, but when you squash them down to 2 dimensions, they get very thick and messy. So there's a lot of interest in chaos these days because most complicated physical systems like the weather or the stock market are chaotic. But the harmonograph, in contrast, is exploring a different aspect of physics. It's producing, at least when it's working well and when there's not much friction, the simplest, most regular sort of curves possible. So the opposite of chaos is another kind of thing called complete integrability. So it means basically that you have a physical system, for example, a couple of pendulums, where for each part of it, like each pendulum, the position and velocity is doing something extremely simple, basically moving around in a circle or an ellipse. So you can completely separate out the complicated system into these individual parts, each of which are doing something extremely simple. Whereas in chaos, every part of the physical system is interacting with every other part, and they combine to do something incredibly complicated and almost unpredictable in practice. So more complicated physical systems would require even higher dimensional phase spaces to describe what's going on. So for example, suppose you have a box of gas. So this is like a little box of atoms bouncing around in a gas. So this is actually a square box here that has 32 dots in it, 32 atoms, you could say. So if you think about that, so to describe the position of each of those 32 dots, for each one, you need to specify its horizontal and its vertical coordinates. It's 2 parts of its position. So it takes 64 numbers to describe the positions of all these dots, 2 times 32. But also, each one has its own velocity. So when you're describing the position and the velocity, you need 128 numbers, twice as many numbers. So physicists have this way of thinking about it, where you think of this big complicated system as a single point moving around in a 128-dimensional space. And that turns out to be a very useful thing, because even though nobody can really visualize a 128-dimensional space very well, the mathematics that we learn from 3-dimensional space to describe the motion of a curve in three-dimensional space, you can easily adapt it to 128 dimensions just by writing 128 numbers in a long list instead of just 3. So mathematicians are perfectly happy to study very high-dimensional spaces using ideas that you have an intuition for from low dimensions. It actually took people a long time to really catch on to the idea that these 128 numbers you would need to describe the positions and velocities of all these dots should really be thought of as giving you a point in a high-dimensional space. People were happy to imagine equations that involve lots of numbers, but it took them a long time to really develop a geometrical way of thinking about them. And so it was really in the late 1800s, the two very important physicists, Boltzmann and Gibbs, who were doing things like studying boxes of gas, really got this geometrical way of thinking about the motion of a bunch of particles as the motion of a single particle in a high-dimensional phase space. And it was actually Boltzmann who in 1871 who introduced this word phase. He didn't call it a phase space, but he introduced the phase idea. And so why phase? Well, if I get to show you some lissajous figures, you'll see that there's a meaning in the lissajous figures of the word phase, and Boltzmann was using an analogy to that idea. So he basically had the idea that this kind of picture was like a souped-up version of these simpler curves that I was drawing. And then in 1902, Gibbs really came out and said that you could think of the motion of a bunch of particles as the motion of a single particle in a high-dimensional space. Gibbs was the first American math PhD, by the way. He got his PhD right after the Civil War. And then it was Henri Poincaré, the French physicist, who first understood that you could think about chaos as the result of something moving around a complicated path in a phase space. So in 1889, he won a prize for a paper where he was studying the solar system, and he showed that if you had a three-body problem, like a star, a planet going around it, and a moon, that could be chaotic. And so he came up with the concept of chaos and thought about it using phase space. There's a very nice article. These slides of mine are on the web, and you can get a hold of them, and you can click on that and read the history of phase space. So chaos is a lot of fun, and it's very popular, but there's also complete integrability, the opposite of chaos, which is what the harmonograph illustrates. And so I have a friend, David Chudzycki, who made this program that lets us do a version of a harmonograph on a computer. And so here what we've got is the equivalent of a pendulum that is moving in two directions, vertically and horizontally. Sorry, two pendulums, one moving vertically, one moving horizontally. I don't know if you can read these little numbers here, but the frequency in one is 3 times per second or something like that, and the other is 2 times per second. So it's moving up and down 3 times for every 2 times it goes back and forth. So this is similar to one of the, similar but different to the thing I showed you before, where we have a 3-to-2 ratio. Actually, I'm sorry, this one is a little bit, I'm sorry, this is more complicated. It's more fancy. No wonder it was looking too complicated. This is what I wanted here. So this is exactly the thing I showed you before, when you have something that's vibrating 3 times vertically for every 2 times horizontally. This is one of these lissajous figures. If I change the number 3 to some other number, you get a different picture. So this would be 5-to-2. So lissajous worked out the math of these figures, and these kind of figures are very, very simple to understand if you're into sines and cosines, which is the kind of math you need to think about them. If you make it not perfectly nice, like 5-to-2, but if you make it, say, be a ratio of 5.01 to 2, well, I did something even more complicated than that, but that'll be just as good. then it won't come back exactly where it won't land exactly where it landed before. It keeps drifting off. Actually, there it's, let's see, somehow I managed to get it back to 5. And so you get a more complicated thing. Here, that's a little bit better. So here you can see that it's not doing it perfectly. It keeps sort of drifting off from where it had been. And so it traces out much more complicated patterns. And these are more like what you'd actually see on the harmonographs here, because it's impossible to get those weights lined up exactly right. So you don't ever get perfect frequency ratios in real life. You get things that are more complicated always. And you can also throw in a third vibration. So that guy there actually has 2 pendulums and a third one which can vibrate in both directions. So that's really acting like having 4 pendulums. That's too complicated for me. But this guy here, this simulation here can do a situation where you have the equivalent of a harmonograph with 3 pendulums. And so when you get the third pendulum vibrating, then you get much more complicated figures than the lissajous figures, but still within this realm of what's called complete integrability, meaning that if you're a mathematician, you feel that like you can completely understand what's going on here. So I think I'll stop now. So it's fun to play around with these, but it's much more fun to do it yourself than to watch some other guide do it. And so we've got physical harmonographs, and we've got theoretical harmonographs, and we'll see which one breaks first when you come up and try to play around with them. I think we have some students who will guard the physical harmonographs to keep you from doing anything too destructive to them, but they're a lot of fun to play with. So thanks very much.
All right. Now, normally we would move to a question and answer period, but we're going to do things a little differently tonight. And we're actually going to forego the question and answer period. And instead, we're going to invite all of you to come and play with the harmonographs.
You can ask questions too there.
And you can also ask questions in a more informal setting, and that is that both John and Anita will be available for you to ask questions, as well as the students who've built these instruments. And there's also some art in the back that you're welcome to look at. And we will also have some refreshments and some other goodies in the reception area. But before I let you go, I need to make 3 announcements of some public lectures. And the first one is next Friday, March the 4th at 7:30. There will be a lecture here in Siegfried Hall that is part of the St. Jerome's 150th anniversary lecture series, and it will be by Lawrence Hill, who is an author, internationally recognized speaker and consultant, and he will speak on identity as performance. You're given a script, but you can switch it, maybe. So that's the first one. The second one is the following Friday, March 11th at 7:30, also here in Siegfried Hall. The lecture is going to be the last Bridges lecture for this season. It's entitled Mathematics, Music, and Visual Arts, and it will be by Nathan Selikoff, who's an artist and programmer from Florida, and Dmitry Timoshko, who's a professor of music at Princeton and author of the book A Geometry of Music. And finally, on Friday and Saturday, April 22nd and 23rd at the Conrad Center in Kitchener, as part of the KW Symphony Intersection Series, will be a concert entitled The Geometry of Music, Harold Scott and McDonald Coatsecker. And this is the Intersection Series is a series with similar goal as the Bridges lecture in connecting 2 different disciplines. And for this particular concert, the connection between math and music is at the forefront. And in fact, the March 11th Bridges lecture and this concert have some connections. And I encourage you to chat with Krista Blake during the reception. Where's Krista? She's right there. And she can tell you more about this particular concert. So Having said that, I will now invite you to come and check out the technology, the art, and interact with our two speakers. And I will finally ask you to join me in thanking both John and Anita tonight for some really inspiring lectures. Thank you.